Okay, here's the instructions on how to use the Wave Edition app that I've uploaded for you. The app will open in a program called Max, so you do need to go and download Max, and I'll have a link to that on Canvas. If you're doing this in the Mac Lab in the library, Max is installed on those computers already. The first thing you want to do is check your options, go to audio status, and make sure that your input and output are correct. And I actually want to make both of those loopback audio because that's the routing thing that I'm using to record this video. But you would probably use, internal microphone, internal speakers. Okay, so the way this thing works is we have some oscillators that will create a signal. So I will make the frequency 200 hertz. Let me turn this on. And then if I turn up the volume, you hear I'll turn that down a little bit so it's not annoying in your ears. But you see we have a wave at 200 hertz. So here's the spectrogram. This is frequency over time, and this is amplitude over time. And I can make it bigger or smaller, that's just a way to see it. So we have here 200 hertz. Now, if I make another 200 hertz sine wave and add it together, what happens is it gets bigger because these waves add together. They add to each other. But what I can do is, let me turn the volume down some. If I put both of these at the same volume, and now I want to make the thing smaller, no, like that. As I change the phase of this wave, I can actually make the wave disappear. So they're exactly out of phase, so they add together to a flat line. And that's what I was talking about in the other video. That's how noise-canceling headphones work. They invert the sound, and they add together. So if I turn this down, you see we have a single wave, and if I get it back to where it matches the amplitude of the other one, we now have nothing. Cool? So the other thing that we can do is, let's make some octaves. So 200, 400, 600, 800, 1000, 1200. I can set all of the volumes to be the same. Let me put this back in phase. So turn the sound on, and we get If we change the volume levels of each one, you see how the waveform changes and also how the timbre of the thing changes, like that. So if we stop this, so you see each of these frequencies is represented in the wave. The big ones are the 200 hertz, and then in the middle is 400, etc. So they all add together to make that wave. So the other thing that we can do, I have this set up to work on a micro. Oh, wait, let me go back here. So this is clean overtones, right? Like we get, oh, here it comes through. You can see there's like each overtone, and it really lines up because these are whole number multiples of each other. But if we start changing these things, you see we get a much more crunchy kind of sound. Let me turn that up, make sure you can hear it. Right, and a much more ragged looking spectrogram. and the wave is also like kind of pretty weird looking. So let me turn all these oscillators down now, and what I'm going to do is turn on the microphone here. So if I turn up the microphone, you now see the waveform reaction to me speaking, and that sonogram is also like way more complicated. But if I imitate the oscillators and go ooh, it looks almost just like the waveform at that thing. Ooh. Okay, that's about as high as I can sing. But if we try to recreate the waveform or the spectrogram from the other video, if I go shh, that's lower energy there. Shoot. So you see, again, sort of like the spectrogram that we had there. So there you go. That's how this thing works. Your assignment for the week is to download this and play with it, and I'll ask you to do a few things and make some observations that will all be described in the assignment. Thanks.